All right, everybody. If I sound excited, it's because we're about to start our discussion of organic synthesis. It's very exciting. But before we can commence, we need to review what kind of a species will give us this result. Yeah. Two boxes, hardly fair. Okay, now, it's one of my favorite test questions. Wow. So I'm telling you the pKeq for this reaction. So already you know what kind of reaction it is. What is it? Acid base. Thank you. Acid base. So what do? You don't give up. You cross off your spectator. You connect the pair that's already there. You talk to me about which one of those two is the acid. The one on the left has the extra proton. What's the pKa of said proton? 25. Okay, so this is a base, right? And they're related, the base to the conjugate acid, which must have a pKa equal. You should know the answer right now. There's only one number that can go there to give pKeq, which is left pKa minus right, has to equal negative 20. 25 minus some number gives negative 20. 25 minus x equals negative 20. X equals, add x to both sides. Yeah, and then add 20 to both sides. No, yeah, 45. I need an acid with a pKa of 45 in the right side box, please. An alkene. And don't make your life difficult. Go with the simplest alkene you know. How about the old H2CCH2? And give me its conjugate base in the box to the left. Take H plus off of it. Now, I crossed off K, so you don't have to worry about it anymore. I don't need any Ks. K was never there as far as my mind is concerned. CH2 double bond, CH with a minus. Please put the minus on the C. Tell me you know where the minus really belongs. Yeah. There you go. Good job. And pKa, the only pKa that works is X equals 45. And I guess just copy everything for activity 4. This isn't too bad. We're not done yet. You know the drill, right? What other things do we like to ask about? Something about the bases, right? Yeah. Green base, pKb, 14 minus the pKa of which pKa? Careful. The first one on the screen? Yeah. The conjugate acid's pKa. That's what I wanted to hear. Conjugate acid's pKa, negative 11. Strong base. Yeah, strong base. You thought that was a strong base. What about this one? What about this one? As he put the second arrow up here, anticipating more questions. 14 minus the pKa of its conjugate partner, 45. Wow, negative 31. That's a wicked strong base. That's the second strongest base you could possibly think of. The strongest base you can think of is alkane conjugate base. And what else do we like to work on? pKeq. Left. pKa minus right. And KEQ. 10 to the 20. Big time, circle the arrow pointing to the right. Huge. In fact, it was more correct to have that top arrow missing at the start, like when I just put it in now, right? When the equilibrium is a big difference, like 10 to the 20, you almost don't want to write the other arrow at all. Too small. Yeah. And I believe that's all we did with pKa's review. And I got excited about something, but all I did was pKa. That's mildly exciting. It's not synthesis though. Okay, I'm gonna show you that. That species you made with an acid-base reaction. Here's a little more information about it. It's a great, if you had to pick Lewis base or Lewis acid, what would you pick? Oh, that's a bad question. If you had to pick, yeah, Lewis base or Lewis acid, that was a great question. Does it have, do you think it wants more electrons or does it want to donate electrons? It wants to donate. It's got extra electrons. It's got an anion. I don't think there's many times you're ever going to say this anion is a Lewis acid, do you? No. You're an electron donor if you have an extra electron. And anions definitely have extra electrons. So I said Lewis base, I hope. Electron donor, Lubnu. And we're not doing, we already did the BB stuff upstairs. This is all about Lubnu. Attacking. Not yet. No, you can stop your copying until I figure out a nice activity juncture. Those are just notes for now. Now, what is this word synthesis? I threw it out there a couple times, right? I need that C- to make a bond to what type of atom for this to be considered a true organic synthesis? In organic synthesis, we make what kinds of bonds? We're making larger structures. That's what synthesis is. And the backbones of organic structures is almost always what type of atom? Carbon. So I need this C- to be attracted to a C that has a somewhat positive charge. What kind of atom must be bonded to a C for that C to feel a somewhat positive charge? A more electronegative atom. Now, you might think oxygen's a good choice. It's not. Like an alcohol, you might think that's a good choice because that makes, don't copy this O. You're not copying anything right now, right? Now, I want to make a carbon-carbon bond, but right now I know this is not going to make a carbon-carbon bond. If I have these two species right here, you're going to get an acid-base reaction. How do you know? How do you know? What's the pKa of an alcohol? 17. What's the pKb of this thing when it gets its proton back? This thing, when it gets its proton back, is here, 25. Acid-base chemistry says if it's possible, 17 will always go to 25. You're going to do an acid-base reaction. You will not be making carbon-carbon bonds. You'll be making carbon-hydrogen bonds. So I liked your oxygen because it was nice and electronegative, but I didn't like the fact that you brought in a pKa less than 25. That was bad news. How about another kind of atom that's also electronegative? And I also want it to be fairly stable when it leaves as an anion. Oh, so I don't like oxygen for another reason. O- is not very stable. Do you know how I know? What does water become after it loses a proton? Hydroxide. Is water a strong acid? The reason it's not a strong acid, you correctly answered, by the way, it's not a strong acid, is because hydroxide is very unstable. That O-, it can't resonate. It's not, it's an anion. It's not happy at all. But I like halide ions. You know why? I know 3 of them are really stable anions. Based on my knowledge of acid base. How do you know Cl minus, Br minus, and I minus are all more stable than F minus? Based on chapter 4, acid base chemistry only. Strong acids, HCl, HBr, and HI mean Cl minus and Br minus and I minus are all stable. HF is a weak acid. We didn't put it on our table for a good reason. It's not a strong acid, and we don't use it too much. But if you need to know its pKa, it's above 0. It's not strong because F minus does not like being F minus. F minus wants to bond with anything. It doesn't even care. If anything has a hint of a positive nature, F minus won't react with it. So pick a halogen that's not fluorine. Fluorine's great. And I need it to be a carbon that's not got too much other stuff on it. So maybe 1 more carbon and a couple H's. That's ethyl chloride or chloroethane. And the most important thing is the carbon being bonded to chlorine. Yeah. And watch this. This should look very familiar. We had a name for this kind of arrow action. Coming in from 180 degrees away from the bond you're breaking has a name. Yes, backside attack. I had one student one semester, he said, back attack. He just loves saying it. He just loves saying it like that. So this is for you, Aladdin. Back attack. I'll write the full thing. Backside attack leads to the excitement. New bond. Oh, yeah. It's doing some funky stuff here. CH3 got pushed up here. And I just made an executive decision. That's such an important picture. That will be your activity, just this box. Yeah. Activity 5. We're not quite done with it. It has a different name in chapter 9. So we're going to get used to that too. SN2. And I know it's not on our next test, but it's the test after, not that far into our future. So outside the yellow thing, I'm going to put the explanation because you don't have to put it on your activity. It's looking ahead. Substitution is the S. This guy here was a nucleophile. So it's a nucleophilic substitution. I'll underline that 4 times. And look at the mechanism. How many molecules were in the mechanism? Molecule A, molecule B, 2. It's called a bimolecular reaction. And some of you have done 142. I think you do some kinetics in there. Yeah, and you talk about bimolecular, unimolecular, and that's about all. You never see termolecular, which is 3. You don't have 3 things happening at once ever. It's one thing at a time. Okay. Yeah. And just when you thought you were finished with a short activity, he's going to extend it. I'm going to extend it. We'll have a slightly different alkyne and a slightly different alkyl halide. And we'll pretend it was a question on a test. Yeah, this is activity 5 still. 5 continued. Just down here. Okay. And we're gonna have to talk about it. Yeah. I think we can copy the stuff from before. What's blue is going to stay blue and green is going to become black. I think we can handle it. So the blue has the isopropyl, C-triple-C. The exciting stuff right here. Why is that exciting? Is that new bond? Back to me. Why is that so exciting? That's synthesis, making carbon-carbon bonds. Exciting. And we're not quite done with that box. There's a stereo center that got attacked. Nah, red's not good. There's a lone pair on the terminal alkyne. It's erasing stuff. It's doing a backside attack on a stereo center that used to be S. Correct? No, it's R. Stereo center used to be R. Any takers on whether the new stereo center is going to be R or S? How'd she know? She said S. She was right.
Because if you change one thing, the stereo center.
Only because it's a backside attack. I'm going to do a pictorial. I'm going to do a pictorial. It won't be part of our quiz or activity, but I'm going to try to show you why R becomes S. So I'm going to make this S. Here's your quickest way. You put your H on. You connect 1, 2, and 3. If it's already R, it's wrong. So I'm putting my H on a wedge. Some adjacent bonds on a dash. And it's now S. So that is the end of the activity. Everything in the yellow box here and here. But I'm going to try to show you. So you have a visual on why stereo centers flip during backside attack reactions, also known as SN2 reactions. Alkyne's just a little bit on the long side. There you go. And my bromide, I'm going to make sure the bond to bromine is here. I'm going to put my methyl here, ethyl here, and H here. And if it's supposed to be R to start with, I like it. Yeah, that's going to be it. Not bad. I'm going to make this. Do you agree that's R? No, it's S, isn't it? Don't agree with me, please. It's dangerous sometimes. Always check. Is that R? That's the better question. And it is, right? 1, 2, 3. R. So let's do a time lapse. Time lapse. This is called a transition state. Wow. Transition state. Fancy. So here it is, just starting to make its bond. Hey, when we start, there was no bond. In the end, there's a full bond right there. What is the transition between having zero bond and having a full bond? I like it. We've already seen a mechanism with quote unquote, not quite half a bond, but we called it a partial bond. Dotted line. That's what I want to be. So you're starting to make a bond to a carbon. And all these groups that were on the left are going to get pushed to the right. So I'm just pushing them a little bit early on here. I'm pushing them to see how they move just a hair to the right. That's a dash. Don't get me wrong, that's not a partial bond. Everything's getting pushed, you see it? My methyl looks kind of lame, but he's back there, he's hiding. And what do you call the bond between carbon and bromine, which started as a full bond? Started as a full bond and ended, I didn't show it, but here it is. When you're done, no bond at all. What's the transition between those? You already gave me the answer, but from the other direction just minutes ago. What is the transition between having a bond and no bond? Say it again. Partial bond. One more transition. Bromine is transitioning from having zero formal charge to -1. What's the transition between 0 and -1? She's going to go like she said before. She already anticipated that. She said partial minus. I was anticipating her saying half minus. But, you know, we don't know if we're halfway yet, is what I'm trying to say. It could be a quarter way. It could be a third of the way. We're partially there. So a partial negative. Yeah, let's put it in something like red. Yeah, pink. The transition between 0 and -1 is partially negative. And we'll do another transition state where it's like 1 femtosecond later. Femtosecond, what is that? 10 to the negative 15 seconds later. Seriously. Still, it's partial. It's not fully formed yet. These keep moving more to the right. This thing is getting real far away. And if you're keeping score, its minus charge is getting slightly more negative. Like that? Once again, outside the box, I apologize. And let's just finish it off. When you're done, you got a real bond. That's exciting. To a C that has a ethyl and a methyl and the H. And I'm sure hoping it's not R. And it is. Did I do something wrong? Yeah, from the very beginning I did something wrong. It's not R. It is R. Wait. 1, 2, 3, it's R. Right? 1, 2, 3. Now it's 1, 2, 3. It's still R. I don't get it. What did I do wrong? Okay. Yeah.
Oh, I think the one.
This got pushed over, this got pushed over, and this got pushed over. Did all those things? Dash.
Oh,
It's an illegal tetrahedron?
No, the dash and ones are not adjacent to each other.
Yeah, I know. It's an illegal tetrahedron. You can't do that, Dr. Whitaker.
Yeah.
Yeah. It's okay. I can edit my diagram just a little bit. Can we do that? I want this to be nice. I'm just going to start with a little better tetrahedron. My apologies. Pointing a little bit down. There you go. And now it's pointing. It's going to get pushed to the right as well. There it is. This was looking pretty terrible. You got to agree with that. Those things were right beside each other. And then it just gets pushed a little more to the right. And then it never crosses over the hydrogen. They both get pushed up. And tidy up here. And get rid of that. Yeah, when you're starting to go to illegal tetrahedrons, things are going to go wrong. Learn from Dr. Whitaker's mistake. And it is now S. And I'm glad you guys cut. That's not in your yellow box at all, so it's just FYI. What is the stereochemical consequence if there is a stereo center being attacked in an SN2 reaction? Then the stereo center will be inverted. R goes to S or vice versa. What is that? Vice versa. Right there. Question mark. Not question mark. Parentheses. And not quite profound enough. 24. Bold. Purple. There we go. Am I losing anybody on the vice versa? Because it's not a common expression, except in science we do use it quite a bit. It just means S goes to R, right? Okay. Inverted could be thought of as flipped, whatever you want to call it. If there's an SN2, stereo center gets flipped. End of video.